Okay, this is chapter 13. We'll be talking about temperature. In order to really take a look at temperature, we need to first take a look at what's going on the atomic level, and that'll let us talk about temperatures and how we measure temperatures. We'll introduce the concept of thermal equilibrium when objects are at the same temperature. What happens when we heat objects up? Well, they're going to expand, so we'll talk about that. And then we'll talk about the ideal gas law, which is going to relate pressure, temperature, and volume, and take a look at some problem solving with that. Then we'll say, hey, if we're talking about gases, we're actually talking about objects that are kind of moving around in the room and they're bouncing, so we'll talk about the distribution of speeds. And then we'll talk about real gases and how we can change the phase, solid, liquid, or gas. So first, the atomic theory of matter. Essentially, all this really says is matter is made up of these very, very small particles that are called atoms. If you've taken a chemistry class, then you know that they're made up of protons, neutrons, and electrons. I don't care necessarily about that so much right now. All I care about is that we have a basic building block of matter, which is atoms. And these guys are really, really, really small. If we wanted to look at the mass of an atom, then we're going to talk about it in terms of atomic mass units, or sometimes you're going to see this written as AMU. And essentially, one atomic mass unit is 1.6 times 10 to the minus 27 kilograms. Now, in about the 1800s, a fellow by the name of Brown noticed that some pollution molecules that were on his microscope slide had a very erratic path. Essentially, what he was kind of onto is that matter is made up of atoms, and these guys are actually moving. So this atom right here has got some speed associated with it, and it's actually going to be colliding with other molecules and kind of taking this weird, bumpy, erratic path. It's moving because it has some temperature associated with it. We can then take these atoms and start to build structure, build matter. If we were to arrange these atoms in such a fashion that they had some very strong chemical bonds between them, then we're essentially going to have a solid material. And in reality, these bonds actually act like springs, so there can be some motion of these particles. They will be vibrating back and forth because they have some energy in them. And a solid is going to have very strong bonds between the atoms. We can also arrange them such that they have weak bonds associated with them. So here I have some matter, and there's some very loose, weak, tenuous bonds between the atoms. And each of these atoms can be moving in different directions. So the velocity vectors kind of show here that these molecules are free to move in whichever direction they really kind of please. This would kind of be an example of a liquid. And if there were no bonds between the atoms, then we're going to have the gaseous phase, where essentially these little whooshies mean that these atoms are moving very fast and pretty much in any direction at all. So there's no chemical bonds associated with them. So these are the three phases of matter: solids, liquids, and gases. Now the first state parameter that we're going to talk about is that of temperature. Temperature is going to be a measure of how hot or cold something is. It's also going to be related to how much energy something has. And essentially, most materials are going to expand when they're heated. I'll give you an equation for that in a couple of slides. Kind of on the atomic level, the reason for that is as I've said, here we have some solid object, and I've just drawn a two-dimensional. We have atoms that are connected by springs, and these atoms are in motion simply because they have some energy, so we can have some motion in that direction right there and there. If I increase the temperature, then I'm increasing the energy that these atoms have, and it can vibrate back and forth with a larger amplitude. So the material is going to expand. You see this in real life when we take a look at things like bridges. Bridges have a lot of concrete and steel associated with them. Heats up, it's going to want to expand. So engineers put in expansion joints such as the one you see right here. Now if you want to make a measurement of how hot or cold something is, then you're going to use a thermometer, more commonly known as a thermometer, and essentially it's just going to measure temperature, how hot or cold something is. In order to do this, it takes advantage of the fact that some property of matter is going to change with temperature, most commonly something like length. So the most common type of thermometer that you're probably already familiar with is just a bulb thermometer. Essentially, you're going to take that, you're going to stick it into, say, your mouth or some water or something like that. The water molecules are moving, so they're going to bump into the bulb. It's going to transfer some energy to the liquid in there. It used to be mercury, now it's alcohol. And then this liquid is going to expand because it's received some energy from the water, so it's going to go up. Similar type of thing is going to be a bimetallic strip, which is going to be essentially just two metals, metal 1 and metal number 2, typically brass and copper. And these two metals are going to expand at different rates. So you can kind of see that the green metal here has expanded more than the blue metal. And if we were to have like some contact switches, kind of like a on-off switch, then we can essentially heat up the metal and it can turn some instrument off. Kind of the deal you see right here in this old-timey looking thermometers are the same type of deal, bimetallic strip. As it heats up, it's going to coil more and more and more and kind of read off the temperature. Now it's great to say, hey, the bulb's going to go up or the bulb's going to go down, but since this is a physics class, we need to be a little bit more qualitative about it. So we're going to draw some ticks on our temperature on our thermometer and say how much it goes up and how much it goes down. There's a couple of different scales that we can use. We can use the Fahrenheit scale, which we typically use in the US. So we could talk about how many degrees the temperature has gone up in Fahrenheit. We could also do like the Europeans do and talk about a Celsius scale. Pretty much they're just different ways of dividing this thermometer up. We will at the bare minimum use the Celsius scale, and I'll talk about another scale that's even more important in a couple of slides. The Celsius scale is based off of the physical world, the freezing point and the boiling point of water. So freezing is 0 degrees Celsius and boiling is 100 degrees Celsius, so it makes much more sense from a scientific standpoint. If we ever need to convert between the two of these guys, we can say that the temperature in Celsius is going to be 5/9 times the temperature in Fahrenheit minus 32. So now let's introduce the concept of thermal equilibrium. Essentially, if we take two objects, let's just say we have object A and we place it in contact with B, so there's some thermal contact, then eventually they're going to come to the same temperature, and when they're at the same temperature, temperature is A is equal to the temperature of B, then we say that they're in thermal equilibrium. Kind of what's going on a microscopic scale is the molecules in A are banging into the molecules in B, and essentially let's just say that B was initially colder, so energy is going to flow from A into B, and all the molecules in B are going to get essentially bump into each other, and then when they're in thermal equilibrium, then all the molecules in A have the same amount of energy as that of object B. The Zeroth law says, hey, if I've got two objects, I've got object A and object B, and if they're in thermal equilibrium, now if we introduce, say, a third object right here, then that object is also going to be in thermal equilibrium with the first two objects. So kind of written out, if the temperature A is equal to the temperature at B, and the temperature at B is equal to the temperature of C, and kind of what we can deduce from that is the temperature of A is equal to the temperature of C. It almost seems too easy. So now that I've talked about temperature, we can come back to thermal expansion and start talking about it using equations. Suppose I've got some bar and it's at some initial temperature T0 and it has some initial length L0. If I were to change the temperature, then now I have this bar and it's at temperature T. Now it has some new length that's going to be L, and it's changed its length by some amount delta L, which is essentially going to be L minus L0. What we can do is we can describe this new length in terms of the original length, and then 1 plus this coefficient of linear expansion right here multiplied by a change in temperature. You can kind of see if the change in temperature is positive, then L will be positive. if L will be larger. If the change in temperature is negative, then L right here is going to be smaller. So to kind of take a quick look at our problem here, kind of ginned up a copper rod that has some initial length of 1 meter, and its temperature changes by a positive 20 degrees Celsius. So I could write its new length to be equal to 1 meter, 1 plus its coefficient of linear expansion, 17 times 10 to the minus 6, so 17 times 10 to the negative 6, multiplied by the change in temperature, which is going to be 20. Type all that into your calculator, and you're going to come up with a new length of 1.00034 meters. So quite small. Solid objects such as copper tend to have a very small coefficient of expansion, so they're not going to change their length very much. We can also talk about volume expansion, which is true for solids, but it's also relevant for liquids and gases. And it's going to look the same way. We're going to have some change in volume, which is going to be some volume minus its initial volume. It's going to be equal to some coefficient of volume expansion multiplied by the initial volume, and then the change in temperature. And in general, for solids, this coefficient of volume expansion is going to be 3 times the coefficient of linear expansion. You can kind of think about some volume going, or some volume of a solid going from that dimension to that dimension. Essentially, it's going to happen in that dimension, it's going to happen right there, it's going to happen along that dimension as well. So in general, the volume expansion is going to be 3 times that of the linear. We can take a quick look at these coefficients for various solids. You can see that this 10 to the minus 6 means that it's going to be quite small for linear expansion. And for volume expansion, you can see for aluminum, for example, it's going to be 3 times. The volume expansion is going to be about 3 times the coefficient of that of the linear. Now, what happens if you have the material and you fix it at both ends? Kind of a bad idea. So here we have one surface, and here we have another surface, and we go ahead and we decide we're going to put, say, a metal I-beam in right here. Then what's going to happen is if the temperature changes, then it's going to want to expand, and it's going to either undergo a compressive or tensile stress depending on which direction you're stretching it in. And we know pretty much we can write our stress, our force per unit area, is going to be equal to 1 divided by Young's modulus, which was E, and then the change in length divided by the original length. This is a Physics 101 equation, or 201 equation. We can then use that in conjunction with this equation, with this expression for the length as a function of temperature, to rewrite the stress, the force divided by area, as Young's modulus multiplied by the coefficient of linear expansion multiplied by the change in temperature.